Let's start by understanding the concept of logical implication. Logical implication is a key concept in logic used to express a conditional relationship between two propositions. It's written as P conditional Q, which means if P then Q. The components of logical implication include: first, the antecedent P, which is the condition or hypothesis. Second, the consequent Q, which is the result or conclusion. Here's an example. First, for everyday scenarios, let P be it rains and Q be the ground gets wet. The implication P conditional Q means if it rains, then the grounds get wet. This is false only if it rains, but the ground doesn't get wet. Second, for a mathematical example, let P be x greater than 5 and Q be x squared greater than 25. The implication P conditional Q holds true because if x greater than 5, it guarantees x squared greater than 25. So you can also see the truth table for P conditional Q, where it's false only when P is true but Q is false. And the rest is always true. Next, let's discuss on how logical implication connects to arguments in logic. An argument is a structured set of statements aimed at establishing the truth of a conclusion. The general structure of an argument looks like this: P1, P2, Pn, conditional Q, where P is the premise and Q is the conclusion. For example, premise 1, if it rains, the ground will get wet. Premise 2, if it is raining. The conclusion, the ground will get wet. This argument can be symbolized as P1 conjunction P2, then conditional Q, where both premises combine logically to lead to the conclusion. Finally, let's explore valid and invalid argument. A valid argument is one where the conclusion logically follows from the premises. This means if all the premises are true, so the conclusion must be also true. On the other hand, an invalid argument is when it's possible for all premises to be true, but the conclusion is false. So, to test the validity of an argument, we use a truth table. For instance, we consider P1 conjunction P2, then conditional Q. The truth table shows all possible combinations of P, Q, and compound expressions. If the implication is a tautology, means it's always true. The argument is valid. So, in our example, since the final column of the truth table is always true, means this argument is valid.
For this video is the role of inference are indivisible tools in logic, serving to obtain conclusion from premise in a valid and orderly manner. They form the backbone of deductive reasoning, enabling us to establish the truth of statements based on established facts or assumptions. Widely used in a field like mathematics, computer science, and psychology, these rules ensure that arguments are logically sound and consistent. We can construct, solve, and present logarithm to the highest degree of clarity and precision in using principles such as modus ponens, modus tollens, hypothetical logisms, and among others. Understanding this rule is greatly important for anybody engaged in logical analysis or critical thinking. There is 8 rule of inference. First, we have modus ponens, modus tollens, conjunction, syllogism disjunctive, contradictions, rule of conjunctive suggestion, rule of disjunctive implication, and syllogism. Others of rule of inference, we have conditional proof, proof of cases, constructive dilemma, and destructive dilemma.
First, let's take a look at the example 1. This question asks us to use the truth table to prove the following argument is valid. The argument that we have to solve is, if she go to school, then it is sunny. It is not sunny, therefore she does not go to school. We can see at the last sentence, we have therefore in the beginning of the sentence, which means that sentence is the conclusion. So the first step is, we have to write each primary statement using variables P and Q, which P is, she go to school, while Q is, it is sunny. Next, write all the premises in conclusion. We can write it down like this. P conditional to Q for the first sentence. The second sentence is not Q. For the conclusion, we have to write not P. Then, to complete this question, using the argument that we made earlier to construct a truth table, because we're only using 2 variables, we have to make 4 rows for this table. The first column is P, which we have to write true, true, false, false. Then for Q, we have to write true, false, true, false. Then we need to determine the truth value for P conditional to Q for each row. Then we will get true, false, true, and true. Next, determine the truth value for not Q. Then we will get false, true, false, and true. We have come to this part where we have to take the third column and fourth column and write it like in the fifth column. True and false, we will get false. False and true, it become false. Next, true and false, it will be false. And lastly, true and true, we will get true. Next, we have to fill in the row for not P. Then we will get false, false, true, and true. Lastly, we will take the fifth column and conditional it with column 6. For the first row, which is false and false, we will get true. Next is false and false, which we will get the same answer, that is true. Then we have true and true, which we will get true. And for the last one is true, and the result is also true. And lastly, we can jump into the conclusion. Because the final column in the table is all true, then the implication is a tautology. Hence, we can say that P conditional to Q and not Q conditional to Q is a valid argument.
For example 2, there are 2 questions that require us to use the rules of inference and equivalent to prove that the following arguments are valid. So for the first question, we have that if P or Q, then R and S for premise 1, and if S, then T for premise 2 and not T for premise 3. So we want to prove that from these 3 premises we can get not P. So first thing first, we need to label those premise as premise 1, premise 2, and premise 3. So the next step is, from premise 2 and 3, we applied modus tollens to remove T, and we get not S. Next, from not S, we apply disjunctive amplification to add not R, so we can get not S or not R. Next, we use De Morgan to simplify not S or not R to get not R and S. Next, we applied modus tollens to premise 1 and 6 to get not P or Q, which we eliminate R and S. Next, we apply De Morgan to the previous premise, which is premise 7, not P or Q, so we can get not P and not Q. And last but not least, we simplified the not P and not Q by using rule of conjunctive simplification, and lastly we got not P. That's all for the first question. Next, same goes to question 2. We classified each equation as premise 1, premise 2, and premise 3. So after we classified the premise 1, 2, and 3, so the next step is from premise 2 and 3, we applied syllogism disjunctive to get P then not R. And next, from the premise 3, we use rule of conjunctive simplification, so we can eliminate not R and we can get not S. Next, from premise 2 and 4, we apply syllogism disjunctive, so we can get P. And next step, we applied modus ponens to premise 1 and 5, and we can get Q. If Q, then R. Next, we apply rule of conjunctive simplification to the premise 3, and we can get not R. And last but not least, we use modus tollens to premise 6 and 7, and last but not least, we can get not Q. So the arguments are valid.
Example 3. Given the following premise: if the machine breaks down, then production will stop. If production stop, then deadline will be missed. If deadline are missed, then client will be dissatisfied. Client are not dissatisfied, therefore the machine does not break down. 1. Write each primary statement using variable P, Q, R, and S. For P, the machine breaks down. Q, production will stop. R, deadline will be missed. S, client will be dissatisfied. Question 2. Write all the premises and the conclusions. If the machine breaks down, then production will stop. We will use the conditional symbol, which is P conditional Q. If production stop, then deadline will be missed. It show Q conditional R. If deadline are missed, then client will dissatisfied. R conditional S. Client are not dissatisfied. Client will be dissatisfied is the variable of S. Then if client are not dissatisfied, it means we have to negation variable of S. Then it will be not S. Therefore, the machine does not break down. It means for conclusion, not P. Question 3. Show that the argument is valid using rules of inference. First, we have to write down all the premises that shown in number 1, 2, 3, and 4. For the number 5, we take variable of 1 and 2, then we use syllogism. Then we will get P conditional R. For number 6, based on formula, we can take variable of 3 and 4 and use formula modus tollens. Then we will get not R. For the number 7, we use modus tollens also and take the number 5 and 6. Then the final answer, we will get not P.
To wrap up, logical implication is a key concept in reasoning and problem solving. It helps us understand the relationship between conditions and outcomes, forming the foundation for building and analyzing arguments. We have looked at how arguments are structured with premise leading to conclusion, and how rule of inference guide us in reaching logical outcomes. Using truth tables and recognizing tautologies, we can evaluate the validity of arguments in a clear and systematic way. The examples we covered show how these ideas are not only theoretical but also highly practical. Thus, understanding logical implication, argument, and rule of inference is essential for sharpening our reasoning skills, whether we are dealing with abstract problems or real-world challenge.